So the next way that we can estimate a derivative at a particular point is if we have a graph of the function. So here we have a snippet of a graph of a function. It looks parabolic in nature, at least in the window that we can see. It might do other things outside of this window. But the point that I want to focus on is right here at 5. So what we want to do is we want to say, given the graph of a function, if all we're given is the graph of the function, so let's call this graph right here our f of x, but we don't know what f of x equals. Like I said, it looks like a quadratic equation or a quadratic function here, but it might do something. It might bend back around. It might actually be a cubic, or it could be any number of types of functions. But given the graph of this function, we can at least do something that will allow us to find the derivative at this point. And it gets back to this idea of a tangent line. So what we can do is we can at least sketch what we think the tangent line looks like, and we can make a pretty reasonable sketch of this. So we can sketch the tangent line, and then all we have to do, because remember the tangent line has the same rate of change of the function at that point. So all we have to do is find the rate of change of that tangent line, which is just going to be the slope of that tangent line. So let's use this technique to see if we can't approximate the instantaneous rate of change of this function f of x at x equals 5. So what we're trying to approximate is f prime of 5. So what I want to do, and I'm going to get a straight edge here in just a second, but if I kind of trace over this function, I get a pretty general idea. And then when I hit this point, rather than following the function, I want to have this same rate of change at that point. So if I'm tracing this, and I can kind of do this just by following the curve. I'm following this curve as I get closer and closer to 5. And once I get to 5, I'm going to say, you know what, that's going to be right about there. And I'm going to call that good and say that that's going to be the tangent line. So I'm going to come over here and do my best to try to sketch this tangent line. And hopefully I get something that looks pretty decent, and you'll be able to see what this looks like. So there's the graph of a tangent line to f of x at x equals 5. And so all I need now is I need 2 points on this tangent line. Well, one of them I already know based on the fact that it's labeled. I'm going to use the point 5, comma 5. And then if I go look at any other point, trying to find where I kind of hit the intersection here, and it looks like I can say, you know what, I've got this point right here, which is at 3, comma 1. And so I can use those 2 points to approximate the rate of change. By finding the slope of this tangent line, I can use that as my approximation for the instantaneous rate of change of f at 5. So I can say that f prime of 5 is approximately equal to, and this approximation is as good as my tangent line. So if I do the old y2 minus y1, I want to keep it positive, so we'll do 5 minus 1 over 5 minus 3, which is 4 over 2, which is 2. So because the slope of this tangent line is 2, I can use that as my approximation for the instantaneous rate of change of this function f of x at x equals 5. I can say my approximation is equal to 2.